Hello AP Chem students and welcome to topic 3.10, solubility. The learning objective here is 3.10.a. Explain the relationship between the solubility of ionic and molecular compounds in aqueous and non-aqueous solvents and the intermolecular interactions between particles. So let's get into it. So before we begin, a thought that will help you reason through this section is like dissolves like. Now let me tell you, this is a memory aid, not a justification. If you are asked to justify why two substances will dissolve in each other, you may not say this, or well, you can, but you would not get the point. You must continue on to a justification that invokes intermolecular forces, which is, of course, the theme of Unit 3. So, also, I have a little bit of preview vocabulary for you. This vocabulary will really come more into play later in the course. We talk more about solubility and what impacts solubility. But in case you hear these terms, I just want to preview them for you now. So we have an unsaturated solution, which is a solution in which more solute can dissolve. You have a saturated solution, which is the point at which the maximum amount of solute has dissolved in the solution. Then you have a supersaturated solution, which is a situation in which you have heated a solution and then cooled it down. So more solute is present in the solution than would be expected under normal conditions. We use this to our advantage when we're doing things like making candy. And then a precipitate forms. This would be if you have a supersaturated solution, then you add a seed crystal, you would see a precipitate form nearly immediately. So if you've ever seen rock candy on the stick, where you got these beautiful kind of crystals, that is done by making the supersaturated solution of sugar, and then putting the stick in there, and the stick has been dipped in a little bit of sugar before they dunk it in, and then they let that cool slowly, and that's how you get that beautiful crystal sugar stick. So solubility. In order for a solute to dissolve, it must have forces that attract it to the solvent. This is best achieved when the IMFs in the solute and the solvent are similar. So for example, solutions between ionic compounds and water form because of the attraction between the water dipole and the charged ions. And the opposite is also true. So we would not expect sugar to dissolve much in water because sugar is a non-polar substance, whereas water is polar. So, sugar is covalent, whereas water is polar. So you would mostly see sugar stay at the bottom, although you do have a little bit of sugar that will dissolve in the water. Now, if we look at some other examples here, here's some colored water and some dyed isopropyl alcohol. Okay, these do have similar intermolecular forces. They both are polar, and actually they both hydrogen bind. So you would see this dark miscible phase is formed by the mix of the two together. If you contrast this with mineral oil and dyed isopropyl alcohol, mineral oil is nonpolar. And so what that means is that your mineral oil would rather form associations with itself than form associations with the isopropyl alcohol. So you do see a tiny little mixing at that boundary, right? Because they do both have LDFs, and so there is a little bit of mixing that can occur, and you can kind of see that there. It kind of looks almost fuzzy. But you see the separation of layers, and that is because they would rather stick to molecules of itself than stick to or associate with molecules of the other species of this. Okay, so while we often think of a solution as being a solid dissolved in a liquid, remember that solutions can exist between all the different states of matter. So we can look at solid, liquid, and gaseous solvents and their different solutes. So you can have a solid dissolved in a solid, and that would give you the appearance of a solid because we would expect the solution to look like the solvent. And so this would be like brass or steel as an example. That's an alloy, which we've already talked about. You can have a liquid dissolved in a solvent, solid solvent, and that would be an amalgam. Okay, you often hear things like that, like with tooth fillings, right? So you often hear that as an amalgam filling. You can have a gas dissolved in a solid, which is harder to think about, but that happens with things like you can have hydrogen dissolved in platinum. You can have a solid dissolved in a liquid, which is what we probably most often think about. So that would be something like a sugar solution. You can have a liquid dissolved in a liquid, like rubbing alcohol. You can have a gas dissolved in a liquid. We see that with carbonated drinks, which we're going to talk about more in just a second. You can actually, believe it or not, have a solid dissolved in a gas. So that would be like camphor in nitrogen. I also saw a laughing gas in nitrogen, which another application at the dentist office. You can have a liquid dissolved in a gas. So that would be like humid oxygen. You can also, fog is another example of this. And you can have gas dissolved in gas, like the air that you breathe. So different substances have different degrees of solubility. Some liquids can mix in all proportions and are said to be miscible or fully miscible. For example, ethanol and water can mix with each other in the entire range from 0 to 100% ethanol. But sometimes you have something that's called immiscible. But even immiscible liquids, which are generally seen as not mixing together, can be shaken and temporarily combined, as they do have some overlapping IMFs, which we talked about just a second ago. So for example, oil and water. I'm going to go ahead and start this video so you can see. But the different liquids would soon congregate together under the influence of their dipoles and hydrogen bonding attraction. So for example, here, we can make them mix temporarily, but you can see that they start to separate out again pretty quickly. And again, that's because the water would rather hydrogen bond to itself than form LDFs with the oil. It's a stronger attraction. So when a water encounters another water, it will hydrogen bond. And then that's why you end up with these clumps of water molecules together, and then they kind of find each other and you see the separation. Okay. And this is all based on energy, right? That's a lower energy state, and so that's why nature settles out that way. So in general, remember the following. Polar or ionic solutions will be the most soluble in polar solvents, whereas nonpolar or covalent solutes will be the most soluble in nonpolar solvents. All right, so let's talk about the solubility of gases and liquids for a minute. So some different factors impact the solubility of gases and liquids. Most gases are less soluble in liquids as the temperature increases. So you can see this here. As temperature goes up, the solubility goes down. Again, this is a general statement. This, for example, is why if you leave a can of soda in a hot car, theoretically it could explode. Now it has to be pretty hot, but that is an example of that. At constant temperature, the solubility of a gas, which we abbreviate as S, is directly proportional to the pressure of the gas. Okay, so this is called Henry's law, and so you can see that here. Partial pressure is increasing, the solubility is increasing. This makes sense because if you increase the pressure, you're increasing the number of gas particles that's in contact with the liquid surface, and so this graphic does a really nice job of showing that. So this is why your drinks start to bubble when you unscrew the cap on the bottle. You've released the pressure that's present above the liquid surface, and so the gas becomes less soluble, and then you start to see the bubbles leaving the solution. Okay, so then we have this law named Raoult's law, which states that the vapor pressure of a solvent above a solution is the product of the vapor pressure of the pure solvent and the mole fraction of the solvent in solution. In other words, the presence of a non-volatile solute lowers the vapor pressure of a solvent, and that should make sense to you as well, because if you look at a pure solvent here, right, a pure substance, all of the surface particles are free to escape the surface of the liquid and become a gas. Whereas if you take up some of that surface area with solute particles that are non-volatile, then they're going to lower the vapor pressure strictly because you have less of the solvent particles exposed to the surface. So the particles cannot escape and become a gas unless they are allowed to be present on the surface. So less particles of volatile liquid are present on the surface, so less are available to vaporize. And that's Raoult's law. So what should you be able to do with this? First of all, determine if two liquids will be miscible or immiscible by considering their IMFs. And second, choose the best solvent to form a solution for a solid solute based on the intermolecular forces. This relates directly to the glitter bottle or the blue glitter lab if you did that. Also relates to the lava lamp lab if you did that. And also there are demos that you can seek out online. My favorite one is potassium permanganate and iodine in water versus hexane. Does a really nice job of illustrating this as well. So go check those out if this is still a little fuzzy to you. And I will be seeing you soon for section 3.11, which will be spectroscopy in the electromagnetic spectrum. See you then.